everybody! Welcome to today's episode of Kinese 101.
Woo!
Today, the crew and I are here to teach you about the sliding filament theory.
Filament theory, filament theory, filament theory.
Gather around, my children. Let me tell you a story about how our muscles contract and relax.
Stop. Wait a minute. Fill my cup, put some knowledge in it. Take a sip, sign a check. Julio, you know it. Sorry, but they needed some background information before we got real.
So remember our friends proteins? All those little munchkins with so many different functions. Just remember that they only follow these two simple rules.
Rule number uno. Proteins like to change shape when compounds bind to them. Rule number dos. Changing shapes can allow these munchkin proteins to bind or unbind with other compounds.
Now that we've gotten that straightened out, let's delve into the world of the muscle belly. As we all know, the myofibril is the smallest part of the muscle fiber in the muscle belly. However, these myofibril strands aren't as simple as we think they are.
These myofibril betrayed and lied to us. In reality, they are divided lengthwise into eensy-weensy, teeny-tiny sarcomeres. On this planet, they are known as the functional unit of the myofibril, which can be then divided into the I, A, and H bands. They are arranged in a stacked pattern throughout the muscle tissue. These instruments are vital to the role played in the muscle contraction, for they house the proteins that enable them to change in length.
There are two types of microfilaments within sarcomeres. There are the star-crossed lovers, myosin and actin! The A bands, as mentioned before by the great storyteller Moi, remain relatively constant in length during muscle contraction, while other regions within the sarcomere shorten. While the H band, which is part of the A band, is composed only of thick myosin strands, the A band is made up by thick and thin, lumpy, overlapping strands of microfilaments of myosin, the lover who anxiously waits to meet up with actin.
Oh, actin, how lonely you are without your lover. Making up the thin strands of the thin filaments within the I bands of a sarcomere, it is the portion of a sarcomere that changes in length. But wait! There are thousands and thousands and millions of sarcomeres. But what exactly separates them? Well, let me introduce you to Z-lines. They form borders of alternating thin filaments in a zigzag pattern, which give the muscle the striped appearance we are all accustomed to.
Did you know the filaments of the I band, the thin strands of actin, attaches to the Z lines? Therefore, when a muscle contracts, the sarcomeres decrease in length, causing the Z lines to grow closer in distance to one another.
So, as mentioned before, these star-crossed lovers, myosin and actin, don't touch, but will do anything to meet each other. However, there are certain obstacles in their way. Let me introduce to you the strong, the mighty, the powerful bodyguards!
Introducing troponin and tropomyosin, the two bodyguards blocking actin from reaching myosin. Warning, 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 intense information collected about these bodyguards by Spy Agent 66248 about to be revealed. Prepare yourself, s'il vous plaît.
Troponin. It is a complex made of 3 regulatory proteins that is essential to muscle contraction in skeletal and cardiac muscles. Tropomyosin. It is a 2-chained alpha helix coil found in skeletal and cardiac muscle. Duty: to inhibit and regulate the interaction of actin and myosin.
Okay. Enough about those lame bodyguards, troponin and tropomyosin, always getting in the way of the star-crossed lovers. Let me introduce you to the two supporters of the star-crossed lovers, actin and myosin, who bribe these bodyguards. Behold, presenting ATP and calcium. Alert, raw information about to be dispensed.
ATP is an organic chemical found in the body which gives energy. The breakdown of adenosine triphosphate into adenosine diphosphate and a phosphate atom releases energy which enables the myosin to grab onto the actin and pull itself, causing the muscle to contract. Calcium is a mineral that is released to bind with troponin, causing tropomyosin to shift from the face of the actin filament, which the myosin head needs to bind with to contract.
As you can see, all ATP and calcium want to do is simply help myosin and actin be stuck together like glue. But wait, hold up. Where is this ATP formed and where is this calcium stored? Well, the nuclei in the muscle cells and mitochondria work together to form ATP, while the sarcoplasmic reticulum has walls loaded with calcium pumps, which use the ATP to save up calcium ions. However, these storages of calcium channels are linked to voltage-sensitive proteins in the membrane of the muscle cell, which make the calcium stay within the sarcoplasmic reticulum.
Now that all the background information is out of the way, we serve you today's main dish. Here's your dish of the sliding filament model.
So, say you just happen to want to contract a muscle, to shoot a basket, to write, to move, to get food, you know the drill. So where in the world does this process start? Well, it starts in the control center of your body, an organ of soft nervous tissue contained in the skull of vertebrates, the brain. Dun, dun, dun! The motion center of the brain sends an impulse, known as the action potential, down the nerve. This impulse travels down the spinal cord, into the peripheral system, and down the axon terminal, the part of the nerve cell that makes a synaptic connection, until it synapses with a muscle cell, specifically the sarcolemma, the outer sheet of the muscle being contracted.
The receptors found on this outer sheet are ligand-gated sodium channels, meaning that when a chemical messenger, like a neurotransmitter, binds with it, it allows certain ions to pass through. In this case, the neurotransmitter is acetylcholine, a chemical messenger that controls the contraction of skeletal, smooth, cardiac, and voluntary muscles. Good thing we have this ability to contract, because otherwise we wouldn't even be able to function. That includes breathing, folks!
The channel opens up as a response to the acetylcholine bonding with the receptors, creating a rush of sodium into the cell as a graded potential, like a tsunami! If this potential is strong enough, it causes nearby voltage-gated sodium channels to open up as well. This action potential zips along the sarcolemma along the transverse tubules. These T tubules are tunnel-like extensions of sarcolemma that pass through the muscle cell while being wrapped around each myofibril.
The action potential continues to travel down this tube, which triggers the voltage-sensitive proteins to link to the calcium channels in the cell's sarcoplasmic reticulum. When the channels are opening, the bribe, also known as calcium, is released and freed. It rushes into the cell through the terminal cisterna of the sarcoplasmic reticulum, which wraps around each myofibril.
Calcium then performs its duty as a bribe and buys off the bodyguard troponin. If you remember, when compounds bind to proteins, the shape of the protein changes. The calcium latches onto troponin, which causes it to pull the other bodyguard protein, tropomyosin, away from the sites on the actin strands that the myosin wants to come in contact with. The tropomyosin swivels and twists away from the actin, making the binding sites of actin exposed. At last! The bodyguards have been dealt with as the actin is now free to come into contact with the myosin, its star-crossed lover. Hip hip hooray! Hip hip hooray! Hip hip hooray!
Now the other bribe comes into play, adenosine triphosphate, more commonly known as ATP. Myosin heads can only bind to the now exposed sites on the actin when a molecule of ATP from the surrounding area is broken down into ADP and a phosphate atom. This causes the myosin head to gain energy and become activated. The myosin head also moves into an extended position, making it form a cross bridge with the actin. Note that the phosphate produced is also released at this time. This is step 1 of the cross-bridge cycle that is found within the overall theory. It is at this stage actin and myosin have finally made contact.
Aww. After the cross-bridge has been formed, step 2 occurs, the power stroke.
Myosin got that power, dun 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 dun.
The myosin head releases the ADP and all the stored up energy from the breakdown of ATP to ADP, which causes the myosin to change shape and perform the power stroke. This is done by the myosin heads moving like oars. They go from forming the cross bridge toward the Z-lines to pivot toward the center of the sarcomere. This pulls on the actin, and as a result, the entire sarcomere shrinks, which contracts the muscle.
Step 3 is cross-bridge detachment. When another ATP binds to the myosin head, the link between the myosin head and the actin weakens. The myosin head must sadly part with its star-crossed lover actin, at least until its next rendezvous. Farewell, my love, actin, until next time, the myosin says. Step 4 is the reactivation of the myosin head. The energy released from the ATP breakdown into the ADP and a phosphate atom reactivates the myosin head. The energy released returns the myosin head back to its original position.
This cycle continues within the theory as long as the binding sites remain exposed on the actin. However, one must remember that the calcium pumps are still restocking calcium in the sarcoplasmic reticulum, so it grabs the floating calcium in the cell. This causes it to unbind from the troponin. When it unbinds, the resulting shape change puts the tropomyosin bodyguards back into place on the actin and its binding sites. It is due to this that the entire sliding filament model may be viewed as a circle due to its repeating parts and components.
Alas, we come to the end of the episode. Thank you for listening to this week's episode of Kinese 101.
Woo!
An easy way for you viewers at home to remember this theory is by listening to Kinese 101's original hit song, The Star-Crossed Lovers. Until next time.
Signing out!
Should you want to move a muscle, the brain is where you start. The impulse travels down the spine and goes right past the heart, through the PNS, the nerves to the axon terminal, the neuromuscular junctions where the impulse done its part. ACH from the axon terminal to the receptors of the sarcolemma bound. Calcium triggered by nerves released and carried through the terminal cisternea of the SR. Each myofibrill's made of 4 important things: actin, myosin, troponin, and tropomyosin. Calcium binds to troponin and gives a great big twist. Tropomyosin moves and actin's binding sites are seen. ATP binds to special sites on myosin heads, moving it to actin where it forms a bridge. ATP is broken down, energy is then released, giving the myosin heads the strength they need to pull. That contraction's tiny will need a lot more force. More actin and myosins pull, and you're stronger than a horse. As they pull, they overlap, and the muscle will contract. Keep going till there's no more room, and then
Deep in the muscles there is the sarcolemma. It may seem hard, but it's not a dilemma. It is what is connecting everything. What you may ask? Let's ask Bing. Answer is all these filaments. Let's talk about the repetition of these filaments. Those are what's called a sarcomere, and that's not where it ends. Each myofibril's got a bunch of these. Sarcomere's got all these lines and bands. Don't get confused because there are a bunch of zones and bands, all of which are used when you contract your hand. First, let's talk about the Z line. It is used to define what you may ask, define the parameters that each sarcomere can mark. Now let's switch it up, yo. From the ends, let's get in the center, bro. In the center lies the M line. That's all about the lines. Let's get to the zones. There is only one where the myosin's at, and that, my friends, is the H zone. Next is only where the actin's at, and that, my friends, is the I zone. Last but not least, there's one last band. It is where there's an overlaps, and now that is the A band.
now your muscles nice and tight and you're doing lots of work. But what if now and then your job you want to shirk? Let's loosen up those muscles by removing ACH. It's broken down by enzymes, so around it cannot lurk. Calcium moved from cytosol back to SR. Actin and myosin no longer are bound. Troponin and tropomyosin go cover binding sites, returning to normal. Actin and myosin relax. As amusing as this is, it's not just a fun game. Our mark depends on this small song. We know you think the same. Know how your muscles work so you can treat them as a queen. They'll take you through both heaven and hell and everything in between.